Hey guys, coming back at you with another lesson. Today's lesson is on difference tables and slope. And I know we just finished diving into the connection between those two, but we're going to go even deeper today. Today's mindset message is that math makes sense. I want you to remember that. It's really easy to get caught up in the middle of like the trenches and slogging through and trying to figure things out, and you forget there's this light on the horizon to realize that everything does make sense, but it takes the work to get there, and that's a good thing. So you can do it, and we just got to push through it. Math makes sense. It always will, but it's not easy, right? Today's learning goals are to understand difference tables a little bit more deeply, and to connect the differences to slope even more. And we say first differences because we're going to actually talk later about patterns where you may take further differences in a difference table. Your prior knowledge today mostly is finding the slope of a line connecting 2 points, and we'll also review finding equations of lines, and then also just how to make a difference table, of course. So let's dive into a review problem. This is one where I would ask you to pause and do this one yourself first before we move on. Okay, so let's actually take a look at this one together. Now, reminding ourselves, well, what's unique about a line? There's a couple things. First of all, its steepness is unique, so it's slope. So we need to know that. For every line, it's important to know that because that's always built into the equation. And that is not given to us, so that's something we'll have to find. Of course, you could identify the rise and run if you graphed them, but we do want to be fluid at this point with calculating the slope otherwise. And if you remember, the slope is equal to, and I'm going to use this delta symbol again. We use that in a difference table to mean one thing, but it does generally just mean change in something in mathematics. So I'm going to say it's the change in y over the change in x. And you can think of that as rise over run, because rise is change in y and run is change in x. You could also do something that you've often learned before. If this was A and B and C and D, you could just say it's equal to B minus D over A minus C. Or maybe you've seen it as like x1, y1, x2, y2. All the above are the same thing. So either way, however you calculate this slope, it's going to be 3 minus negative 4 is 7, and 0 minus 4 is negative 4. So our slope here is negative 7/4. Now we have two options. We actually have the y-intercept already given to us, so that's pretty nice. So we could use what we've learned before. Y equals, you could use, often we'll use mx plus b. I like to generalize it actually because we'll see how this comes into play later, but I like to call it ax plus b. And A represents our slope, if you remember, and this number added at the end represents our, I guess, our starting point, which is our y-intercept, if you think about the graph. So this would be 3, that's given to us, and we already figured out the slope of negative 7/4, and there's an equation for this line. Don't forget that's not the only way to make an equation. In fact, this one's very peculiar. It's only if we know the y-intercept we can even use this. A more general and sometimes useful format would look like this, and these are the same. Y, I don't care which one of these we use, let's use this point. Y minus negative 4 equals negative 7/4 times x minus 4. And we could realize that minus negative 4 just turns into adding. So y plus 4 equals negative 7/4 times x minus 4. And this one, if you actually solved it for y and simplified it, you'd see that it's exactly identical to this. Okay, so there's a little bit of review of lines, and we'll use that to jump off into our next segment here, another example that's related to this. All right, let's look at our next example. This says, finish the difference table. The differences are constant, so we're going to assume the differences are constant. Whatever this is, it's the same number the whole time, right? And we saw last lesson that that means it must be a linear function, aka its graph forms a line, right? All the points that fit the equation all line up in a perfectly straight line. So this looks familiar actually. This is a table we have seen in the past in an exercise that you did, and maybe it was a little bit of a challenge to try to figure that out at the time. But hopefully this also looks a tad bit familiar to you from example 1, because if you notice, 2 points that are given to us here are 0, 3, and 4, negative 4. This is just a different way of representing that same information. In math, it's really important to realize that we have various representations of the same idea, and there's different insights we can get from each representation. So before we had just 2 points, we made equation, we've used methods we've learned in the past, but now we're kind of breaking it down, or maybe you can think of spreading it apart and looking at some points in between and what those are going to have to be and stuff. So you may already realize, wait a minute, we already figured the slope out, Mr. Engel. I know exactly, because we've realized the slope and the difference are the same thing as each other. So you maybe already thought about that. But we are going to talk about another kind of methodical way to figure out what this difference is if we're missing some things in between. And one thing we can use, but we use in math often when there's something that's unknown, is a variable, right? So this right here, our difference, isn't really known, but we can assign it a variable. In this case, we can use d for difference. And of course, I don't know any of the differences here, so I guess since they're all constant, right, it's the same, I could just label each one of these d the entire way down, right? And the cool thing about this is, again, even if we don't know these exactly right now, we can say that, remember that this plus this gives me this always. So I could call this 3 plus d, right? But then from here to get to the next one, it's going to add another d. So I have 3 plus d to get me here, which makes 3 plus 2d. Basically, we're accumulating copies of d the further along we move in this table. So this becomes 3 plus 3d, right? And then finally right here, whatever this negative 4 is, it's going to be equivalent to 3 plus 4d. And that's nice, because what it tells us is that there's an equation we can use to set up to figure out what that constant difference is, as long as we know some later value down along the line. So we know 3 plus 4d must equal negative 4. So this is kind of on the side. And if I solve this and subtract 3, I get 4d equals negative 7. And dividing by 4, d must be equal to negative 7 over 4. And that's exactly the slope that we had figured out in our last example, right? So in this case, if I were to finish filling the table out, and I'm going to kind of cheat a little bit, and I'm not going to write it all out, but wherever there's a d here, it can be replaced by that negative 7/4, so that's identical the whole way down. And then this right there, you could just plug it in and simplify those things to get the exact values that go in between there. And you'll realize, since that's negative 7/4, none of these in between are going to be very nice values. A benefit of this method that we're doing right here, it's more methodical than just looking at it and kind of guessing or whatever, is, it works especially when these numbers aren't just nice numbers, right? So this is a super useful way to do this. Now there's a little side note I want to talk about here in this example. We can actually use this table set up with these d's to kind of prove that the slope is the same as that constant difference actually. And that's actually using the slope formula we just reminded ourselves of in example 1. And let's just say we choose, any two of these points. Let's say 1, 3 plus d and 3, 3 plus 3d, let's say. If I want to actually calculate the slope, we realize, remember, it's change in y over change in x, right? So that would actually be the change in y just means the difference between the y values and then the difference in the x values. So I could do 3 plus d minus 3 plus 3d all over, what are the x values? 1 minus 3. 1 minus 3. And then what I get here is 3, let's subtract 3 minus 3 is gone. D minus 3d gives me a negative 2d on top, and 1 minus 3 gives me a negative 2, and guess what? Voila! Those negative 2's cancel out, and we can see that we calculated the slope is exactly d. And of course, whatever that constant difference is our slope, like we said before. So that's kind of cool. Let's move on to, I think, just 2 other examples, and then we'll be finished with this lesson for today. All right, these examples, I want you to pause and do them on your own, and then we'll come together and check our work. Okay, so let's go ahead here. Find the constant difference in this table. This is essentially the same as example 2 was, but kind of doing practice on your own. So this one's interesting because, you know, there are ways we could figure this out without that method, but there's quite a few inputs, outputs that are missing here in between. So it's going to be really helpful to think about this. And we can see, okay, if we call this d again, then this is negative 3 plus d. This is negative 3 plus 2d, negative 3 plus 3d, right? And notice the correlation between this input and how many d's we've added, you know? So if I'm going to be at input 10, what should 37 be equal to in terms of this? Negative 3 plus, we can see that this is going to be the same as negative 3 plus 10d. So on the side here, we can just do negative 3 plus 10d equals 37. And I think if I add 3 over here, I get 10d equals 40, and therefore d equals 4. And we've got our answer. Find the constant difference. That constant difference is going to be 4 the whole time. I'm just adding 4, adding 4, adding 4. All right, number 4 says, could a linear function fit this table? Why or why not? Well, hopefully something came to your mind here that we've been learning recently, and that is if it's going to fit a linear function, or if a linear function is going to fit this table, what must be true about the differences? They must be constant, right? So we're going to maybe it's super helpful to answer that question. Could the differences be constant? That's like an equivalent question to this, right? So that's what we're going to try to answer is, could that be constant, right? Well, let's go ahead and add in a delta column here. And it looks like we can figure out one of these right away. From 8 to 11, that's 3, right? And I guess I'll use my red color for new work. But then from 0 to 8, I guess we may, I don't know, we may have to employ what we thought about over there actually. If this is D and D, right? So if I have to add D, 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 so there's 3 D's, right? So 0 plus 3D is going to have to get to 8. And 0 doesn't have any effect, so 3D equals 8. But what do you notice the D value would be there if 3D equals 8? It's 8/3, and 8/3 is close to a difference of 3, but not quite. So, since, I'm going to have to move my little ball here, since 8/3 is not equal to 3, then we have the conclusion that no, a linear function would not fit that table because we need to have constant differences. That's it for this lesson. Happy math, and we will see you next time.